Okay, so notice for this worksheet, we're just going to be working with projectile motion where the object is being launched horizontally. So this is going to be the object's trajectory here. Notice that it's only got a horizontal component, a velocity component here. If it's being launched horizontally, what does that tell you about the initial velocity in the y direction? Well, there just wouldn't be any. So just to let you know that piece of information, once again, we're just going to be launching this object horizontally. So this is the object's trajectory. All right, let's go through this problem here and pull the given pieces of information. Once again, like I said before, well, before getting into that, don't expect to be able to do all these problems on the worksheet that I provided. I would highly suggest working on lined paper. You're probably not going to have enough room to be able to work this completely out on the worksheet that I provided. So also for these projectile motion problems, I would ask your teacher for a sheet of paper if you didn't bring a notebook or whatever the case is. So yeah, just don't expect to be able to do these problems pretty quickly, smoothly for the space that I provided you. Anyway, getting into this, the first thing that we're going to do is get used to the structure of how we're going to be pulling out this given information. Like I said before, the quantities that we're going to be pulling out for is going to be the initial position in the x direction. Same thing with the final, VF, I'm sorry, VX. And then we have initial in the y direction, final in the y direction, initial velocity in the y direction, final velocity in the y direction, our acceleration due to gravity, and our delta t. The whole reason why I put delta t in the center like this is because it doesn't really have to do with either the x or y direction. It just is kind of by itself. It doesn't really have any sort of direction included in it. So this is the structure. We're going to start pulling out our given information. A stone is thrown horizontally at this velocity. What is this velocity telling us? Well, that's going to be the velocity in the x direction. So we have our 15 meters per second from the top of a cliff at this height. Okay, well, that's our initial height. How long does this stone take to reach the bottom of the cliff? Okay, so how long does it take to reach the bottom of the cliff? Oh, so we're looking for our delta t, okay? And how far from the base of the cliff does a stone strike the ground? Well, that sounds like it would be our xf. Okay. And what would you say that the initial, so we have, it's starting off over here. So this is our xi, and then this over here is going to be our xf. So our xi, what would you say that the value is going to be for that? I would just say that our value for our xi is going to be equal to 0. And what about, well, if the object is starting up over here, and then it's going to go down, 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 what would you say that the yf is equal to? The final height. It's also going to be equal to 0. And once again, for our initial velocity in the y direction, are we given an initial velocity in the y direction? It's horizontally being shoved or tossed out, thrown to the right. There is no y component in the initial velocity. So once again, we are going to see that that value is equal to 0 meters per second. Acceleration due to gravity, always negative 9.8 meters per second squared. Are we given the velocity at which the object strikes the ground? No. Nor are we being asked for it, so that's kind of one of those quantities that we don't really care about. Okay, so we're going to be, that's a peaceful information. That's a great piece of information for us to be able to determine which kinematic equation that we're going to be using. All right, so once again, we do want to find out what our xf is equal to. So the only place that we have xf in our kinematic equations is right here. I didn't really circle that all too nicely, but we have that right there. Okay, so we know that we're going to be having to use equation number 1. But we also have our delta t, which is another quantity that we're going to need to find out. So if we have two unknowns in that one equation, that means that we're going to have to find our delta t first, and then plug that in to this equation to be able to find out what our xf is equal to. Okay, and also the problem does tell us to find how long this stone takes to strike the ground. Okay, so the very first thing, we're going to be finding this. So number 1, let's find out what this is equal to, and then 2, we'll find out that right there. Okay, so once again, the quantity that we don't care about is the final velocity in the y direction. So wherever we see that, we're going to say we don't care about these equations. So all we're really left with is equation number 4. So we're going to use that to find out where our delta t is equal to. Okay, so let's just plug this in. Let's go from here. All right, so we have yf Okay, so now we have all of our, now all we need to do is plug in from here. Okay, so we have our 0. And 0 times any number is equal to 0, so we know that this quantity is going to be nothing. Whenever you're dealing with a negative, I typically like to wrap it in parentheses, and the delta t is what we're going to be looking for. So it's nice, the idea that it's going to be 0 multiplied by our delta t. Otherwise, we'd have 2 delta t's in this one equation, making it a little bit more, we'd have to think about this a little bit more. But being that this one delta t is being multiplied by 0, that quantity obviously is that factor is no longer there. All right, so let me just rewrite this over here. So we have this, and 1/2 of negative 9.8, that gives us a negative 4.9 times our delta t squared. Don't forget that squared. I see that a lot where people forgot to drop down this squared as they're going through the problem. It causes a lot of issues. Anyway, so we have two terms over here. I'm sorry, I meant to call this a term that we got rid of. But anyway, we have 2 terms over here. Let's get rid of this positive 44 by subtracting out on both sides of the equation. These 2 will cancel each other out, leaving us with this. Times our delta t squared. Okay, so now we have a multiplication of negative 4.9, so we have to divide both sides by our negative 4.9 on both sides of the equation. Those 2 cancel each other out, and we're going to be left with this. Sorry about running out of room over here. So we have, just coming back up over here, let's say that it's 8.98, and that's equal to delta t squared. We don't care what delta t squared is equal to. We only want delta t. So therefore, all we have to do is take the opposite of a square on both sides of the equation, which is the square root. And I'm just going to do a little bit of rounding here. What's the square root of essentially 9? That's going to be equal to 3 seconds. All right, so we have our first quantity. This is the first thing that we solve for. All right, and like we said before, we wanted to also find out what our xf is equal to. So being that we have our delta t, we could solve out for using this first kinematic equation, we'll be able to find out what xf is equal to. So I'm just going to do that up here. Oh, I didn't mean to put in. Okay, there we go. And we have this subtraction of 0, which gives us no value whatsoever. So we could just look at it as xf divided by 3. How do we get rid of a division of 3? Multiplied by 3 on both sides of the equation. These two will cancel each other out, leaving us with xf is equal to 3 times 15, which is equal to 45 meters. And that's it for this problem.